Okay, today we're going to talk about section 3.6 force oscillations and resonance. However, for this video, I'm calling it 3.6 part 1. We're just going to talk about undamped motion. So we'll be covering pages 1, 2, and 3 of section 3.6. The remainder, which involves damped motion, will be covered in a second video, part 2. So section 3.6 is called force oscillations and resonance. It's going to give us some applications for non-homogeneous equations. So we're going to heavily rely on your knowledge from section 3.5, where we learned how to run through rules 1 and 2, depending on if you have duplication or not, in order to find a particular function. And then, of course, adding the complementary solution and the particular function together to get the general solution of the non-homogeneous DE. So just to kind of recap where we've been and where we're going, in section 3.4, we talked about both damped and undamped motion in a mass spring system. So we were talking about simple harmonic motion, and in those cases, we had the following equation, mx double prime plus cx prime plus kx equals 0. Now, if you'll recall, when we were talking about undamped motion, that means that the c term is 0. So in the case of undamped motion, we lost that middle term. However, if we had a damping coefficient c, then we picked up that first derivative. The difference in this section is now we're going to assume that we have some extra force or external force, which we're going to denote by f of t. Now, theoretically, f of t could look like anything. However, in this section, we will focus on only cosine and sine functions, which we see down here below. This is because we're talking about rotating components where the centroid is off center. So the book gives the example of a flywheel. I like to think of a washing machine where your clothing gets kind of offset in the bin, and then it starts sounding like a rocket ship ready to shoot off into space because that center of gravity is off kilter. So we'll be working with either a sine or cosine function in this case. One thing that I want to draw your attention to is the fact that the textbook is using omega as the weight inside the sine and cosine functions. We're later going to see omega pop up again, but with some subscripts. So I just wanted to call your attention there. All right, so in this video, we're going to focus on the undamped force oscillations. So again, that just means that the damping coefficient C is 0. So in this case, you'll notice that we don't have an x prime term in between here, and so our differential equation simplifies to what we have written right here. Now, if we were going to solve this by hand, what we would want to do is consider the associated homogeneous equation, which would be mx double prime plus kx equals 0. Typically, we would divide through by that m coefficient. And then if we set up the characteristic equation, we would get r squared plus k over m equals 0. And so the roots of our characteristic equation would be plus or minus the square root of k over mi. We're going to get imaginary roots here. So we know we set those up in terms of a sine and a cosine. And so you'll see that's exactly what we have set up for this complementary function, where here omega naught is going to be this square root of k over m. So again, I just want to point out the difference between omega naught down here as opposed to omega up here. So if it's a single omega, that's referring to the function f of t. If it's an omega sub 0 or omega naught, that's referring to the weight inside of sine and cosine in the complementary function. All right, so this omega naught has its own name. It's called the circular or natural frequency of the system. And then if you divide through by a 2 pi, we call that the ordinary frequency. So if you see those terms pop up, now you're aware. All right, but let's go back up here for a moment. Thinking back to section 3.5, we just found our complementary function. We would now want to check for duplication. So if we focus now on our f of t function, which was given in general as f naught cosine omega t, we want to list our terms. So Dropping the coefficient in front of the cosine, we get cosine omega t. Again, it's fine to drop that coefficient because we're going to take a linear combination and that f naught would get absorbed. And then its derivative is going to kick out an sine omega t, and that's it for our terms. So what we want to do, thinking back to section 3.5, is we want to compare these terms with the terms up in the complementary function. And so you'll notice that we have a sine and cosine in each of them. The key here is, how does omega relate to omega naught? Are they the same or are they different? And that's what's going to determine duplication or not. So let's take a look here at case one. The first case is, what happens if omega and omega naught are different? Well, referring back to section 3.5, that means that we have no duplication. So that means that as an intelligent guess for our particular function, we're going to take a linear combination of all of the terms, which is going to be a cosine omega t plus b sine omega t. All right, and so then to determine what a and b are, we would go through the method of undetermined coefficients. So what that means is we would be taking the first and second derivative and then going back up to this original equation here that I just circled and plugging in those derivatives accordingly, and then setting up a system of equation based on the coefficients to determine what a and b are. Now the book has already gone through and done this for you. You'll notice that they get this coefficient right here, f naught over m divided by omega naught squared minus omega squared times cosine of omega t. So I'm not going to go through this derivation, but we will see it work out in our example. But what's important here is, that our sine term dropped out, which means that b is always going to go to 0. And then recalling that in order to find the general solution for these non-homogeneous DEs, we need to add together the complementary and particular function. We get this final general solution here, x of t. Now again, recalling back to section 3.5, the book preferred oftentimes to combine these two trig functions to a single cosine function. So a lot of times you'll see that again. And so at the top of the next page here, we see that if we want to combine it to this single term, we need to use that C equation and that same alpha equation. So again, no need to memorize these. I will provide these on exams or quizzes as needed. Just make sure that you are confident in being able to combine those two appropriately. All right, so this is kind of the best case scenario where omega naught and omega are different and you don't have any duplication. Of course, there's this interesting case where they're actually equal, but we'll get to that in a moment. Case 2 says, what happens if they're almost equal? So let me scroll back up here just for a moment, all right, and look back at this coefficient on xp. What we have in the denominator here is the difference of the squares of omega naught and omega. And so coming back over here, if omega and omega naught are really close to each other, that means that this difference here is getting really small. And what happens when that difference gets really small? Well, then the overall fraction gets very large. And so there's a series of manipulations here. First, they're multiplying through by m. So multiply by m, and then they're dividing by k. And then finally rewriting the constant with a row there. And they talk about the static displacement and the amplification factor. But again, the important part is that that coefficient there is tending towards infinity due to the fact that if these guys are really close to one another, their ratio is about 1. And so that denominator is getting really close to 0. So this is, when this happens, this is called resonance, okay? So you'll see this term resonance in some electrical engineering courses, perhaps even as early as this semester in your circuits course. And so I wanted you to be aware of that if you run into it. So now let's look at this interesting case here where omega and omega naught are equal. Whoops. In this case, we're going to have duplication of terms. And so if you think back to rule 2 from section 3.5, what we needed to do to get out of duplication is multiply by the lowest power of t so that you're no longer being duplicated in the complementary function. Now, since we only had a single sine and a single cosine in the complementary function, multiplying by a single t is good enough. So our particular function is now going to take on the form a t cosine of omega naught t plus bt sine of omega naught t. So again, multiplying each of those terms through by t. All right, and so again, kind of fast forwarding to the solution, I'm not going to go through the derivation, but if you went through and solved for those coefficients a and b, you'll notice that only the sine term survives. This implies that a is always going to 0 because the cosine term isn't showing up, and we get this new coefficient in front here, f naught divided by 2m omega naught. In this case, we have a special term for it as well. What happens is, because of this t in front, as t increases, the sine function continues to bounce up and down, but this t out in front is going to blow up the entire function. And so the amplitude increases without bound. This is called pure resonance. So no longer are you bounded by some oscillating function. It still is oscillating in a sense, but it's oscillating and getting larger as time marches on. All right. So to finish these notes, we're going to take a look at example 4. We want to find the whole solution, right? The complementary and particular function, add them all together for this initial value problem. You'll notice that the book wants us to write it as a sum of 2 oscillations. So we want to condense the sum of the sines and cosines together. So first what we want to do is we want to consider the associated homogeneous DE by setting the right-hand side equal to 0. And then from there, set up your characteristic equation, r squared plus 25 equals 0. That admits 2 complex roots plus minus 5i. All right, so since those are complex, we set up our characteristic equation in the following, or not our characteristic, our complementary function in the following way. We get a C1 cosine 5t plus C2 sine 5t. And by the way, shout out here to all of the t's involved. T is now your independent variable. We're used to working with y of x, and the book pulls a fast one on us by switching it to x of t. So make sure you keep track that t is your independent variable, x is now your dependent variable. All right, so we're going to keep this complementary function for later, and we're going to use it to identify if we have any duplication. So now let's focus our attention on the function f of t, which is 90 cosine of 4t. From that, we want to determine the terms that are going to make up our particular function. So we have cosine of 4t, and we also have sine of 4t. So in other words, our omega naught here is a 4, and up here, our omega is a 5. So because those omegas are different, we notice that we don't have any duplication between the terms and x sub c. So no duplication. I really prefer that you guys get into a habit of writing this out. No duplication or duplication, to make sure that you're checking for that to identify if you need to use rule 1 or rule 2 from section 3.5. All right, since we don't have duplication, we can set up the particular solution, which is going to be a linear combination of those 2 terms. So a cosine 4t plus b sine 4t. All right, so now what we want to do is we want to solve for those coefficients a and b. And in order to do so, we need to remember what is the definition of a particular solution. The particular function is a solution of the original non-homogeneous DE. Solution of non-homogeneous DE. So that means we should be able to plug it back into this original DE right here that I'm highlighting, and then we can equate coefficients. So just to make a note, plug into original DE. All right, so in order to plug it into the original DE, I need to calculate the second derivative. So we'll start by taking the first derivative, which is going to be a minus 4a sine 4t plus 4b cosine 4t. And now let's find the second derivative as well. That is a minus 16a cosine 4t plus 16b sine 4t. Oops, and I made a sign error there. That plus should actually be a minus. There we go. All right, so plugging it back into the original DE, we have the second derivative, which I'll recopy here. Plus 25 times the original particular function. And all of that needs to equal 90 cosine 4t. All right, so then combining like terms, we have 9a cosine 4t plus 9b sine 4t, and that equals 90 cosine 4t. And so what I'm going to do, just to kind of emphasize that we're missing our sine function, is I'm going to write a 0 sine 4t. And so now I'm going to equate the cosine coefficients and the sine coefficients. So if we equate the cosines, we get 9a equals 90, in which case a equals 10. And if we equate the sine terms, 9b equals 0, so b equals 0. So let's pause for a moment here and just double check if this makes sense with what the book had derived earlier. So I'm going to scroll back up. Okay, and so the book had determined that number one, the sine function was going to drop out, the b was going to be 0. That definitely checks out with what we have. And then let's go ahead and copy this down. Let's see if the coefficient that we just found, which was 10, if that matches this term f naught over m divided by omega naught squared minus omega squared. So let me write that down. F naught over m divided by omega naught squared minus omega squared. And so let's just see what this is. So remember what each of these coefficients stands for. The f naught is the coefficient in front of the cosine here in the original problem, which is 90. M, of course, is the coefficient in front of x double prime, which is just 1. Omega naught, do I have those backwards? Let me flip back up here again. Nope, that's right. Omega naught squared minus omega squared. So omega naught is going to be 4. So we got 16. And then we got here minus 5 squared. So this is 90 over a negative 9. We get negative 10. So did I make a mistake somewhere? Maybe I'm calling these by the wrong name. So let's, oh yeah, I think I did switch these around. So let's go back up here real quick. Did I switch my omegas? Omega is what's inside the original f of t function. So let me see if I have those mismarked here. Yes, I do. So let me write this in red. This is a correction from the notes up above. This is omega naught right here. This is omega. So my apologies, I did make a mistake there with the omegas. So these should be flipped around, making this a positive 10. There we go. So we just confirmed that the coefficient that the book had derived does in fact match with what we just found for A. All right, so now what we have just determined is our particular function is 10 cosine of 4t. Now for the general solution, we want to take the complementary function and add it to the particular solution. So that is C1 cosine 5t plus C2 sine 5t. And then adding on what we just found for our particular is a 10 cosine 4t. All right, we're not done yet. We need to now solve for these coefficients. So let me scroll up once more and just look at those initial conditions here. So we're using the fact that x of 0 equals 0 and x prime of 0 equals 90. So let's start first here with x of 0 equals 0. So I'm going to plug that into the equation directly above. That gives me a C1 plus 0 plus 10. So we identify C1 as being negative 10. Now, the second initial condition was that the derivative at 0 equals 90. So let's go ahead and compute the derivative. That is, chain rule here. That's going to be a negative 5 C1 sine 5t plus 5 C2 cosine 5t minus 40 cosine 4t. All right, so now plugging in 0, all of our sine, undo. All of our sine terms drop out, but the cosines live on. So I get a 5c2 minus 40, and that has to equal 90. All right, so what I get here is 5 equals 130. So what am I going to get there? Let's see here, making sure this is panning out. Let's see. Whoops, first of all, I dropped my C2. And let me just make sure that I have this all correct, because for some reason that isn't looking familiar. So we took the derivative of cosine, popped out a 5, did the same for sine. Oh, there's the issue. I found it. This should be a sine. All right, so when I took the derivative of cosine here, I did the chain rule, but I forgot to make this a sine. So that does in fact drop out. And so let me make this correction here in red. This 40 is not here. So I have a 5 C2 equals 90. I apologize for that error. And so now I have C2 equals 90 over 5, which is 18. All right, so to recap, where we're at is we have that x of t equals a negative 10 cosine 5t plus 18 sine 5t plus 10 cosine 4t. Now remember, the book told us to express this as the sum of only 2 oscillations. So we want to condense these first 2 terms. So we have A is negative, B is positive. So I'm going to scroll back up to our definition of alpha so that we can identify what alpha is. When A is negative, we need to add pi plus the tangent inverse of B over A. All right, so let's keep that in mind. First of all, C is always the square root of a squared plus b squared. So that's going to be the square root of 10 squared, which is 100, plus 18 squared, which is 324. So we get the square root of 424. That can simplify. You can factor a 4 out of there. So 2 root 106. And then that alpha we said was pi plus tangent inverse of b over a. So 18 over negative 10 is a negative 9/5. I don't even worry about plugging that in my calculator. I'm just going to leave it as a tangent inverse function. That's an exact answer. And then finally pulling it all together, our x of t function is 2 radical 106 cosine of 5t minus that alpha. And then finally adding on our particular function of 10 cosine of 4t. So there is our entire solution for this initial value problem. So this is going to conclude part 1 of section 3.6. You can move forward to part 2 to see the next few pages of the notes, which is going to be over the damped forced oscillations.